it's always a good idea to read the book. You paid a fair amount of money for it. There's a lot of good stuff in there. And research shows that students that read the book do better than students that don't. It's kind of a no-brainer. So there's good stuff in there. So here's my version of some stuff in the book. So we're in chapter 6 right now. Chapter 6 is about applications of integration. And just a note about where we're headed. So we've got the basics of integration down. We know the definition of an integral is the limit of Riemann sum. We know the fundamental theorem can help us much more easily than Riemann sums can, because they are very difficult. However, the fundamental theorem relies on us being able to identify an antiderivative based on derivatives. What happens when we can't do that? And so there's going to be a lot of functions that we see for which the substitution method, which is our most powerful tool at this point, will not work. So what do we do? Chapter 7, after we do some applications here, we'll then go and try and solve some functions that we couldn't before. So for example, just a brief look ahead. If you tried to integrate, how about x squared times the sine of x dx? No substitution you try will work on that. So what the heck do we do? Turns out there's other tools at our disposal. Sine of x divided by x. Can we find an antiderivative of that with some other tools? Or is it possible for a given integrand, is there no fundamental antiderivative ever with what we know how to do so far? And it turns out sometimes there is an antiderivative. We just don't have the tools yet. Sometimes there isn't an antiderivative, and somebody has to figure out that there isn't an answer to that problem in the ways we've been looking. And so new math gets invented based on that. So this first one here is an example for which we will find a technique to solve it in chapter 7. Or is it chapter 8? Chapter 8, I'm sorry. Chapter 7 doesn't have much in it. We're going to fly through just a couple sections there in chapter 8. This one right here, it turns out in this course there are no techniques for coming up with an antiderivative. And if you want to try and solve this one, then take Calculus 3. We introduced some new tools there. If you're not taking Calculus 3, I'm sorry, you're missing out on some really cool stuff. But that's all right. There's only so much cool stuff you can do in a lifetime. Okay, so that's coming later. But for now, we're just going to play with applications. Some of the applications are going, or most of the applications are going to be physical, in that we're going to be looking at physical objects, or we're going to look at aspects of physics, like work and pressure, for example. So 6.1 is what we need to look at right now. So section 6.1 is about volumes in two different ways. And 6.1 is pretty beefy. It should really be 2 sections. The first part's not too bad. It's volumes using cross-sections. We'll start with that. So that's part 1. Part 2 is volumes using rotations. Okay, so I'll give you an example of each one right now, and then we'll go and do some calculus with them. You've all seen boxes before, right? Now that we have Amazon, I think there's more boxes on the planet than ever existed in the last like 50 years, just this year alone. So a box has a volume. We generally measure the volume of a box by identifying a length, a width, and a height. And we hope that the length, width, and height are perpendicular to each other, okay? So that the length and the width in this bottom plane or the top plane meet at a right angle, and that, say, the width and the height or the length and the height meet at right angles. Right? That's essential to the way we calculate volume. For example, if this were, say, a box, let's use a small box, 5 centimeters by, maybe that's 8 centimeters, and maybe that's 5 centimeters in height. Then the volume here would be, what, 200? Looks right. 200 what? Centimeters cubed, cubic centimeters. So these little tiny centimeter cubey things would fill this up. Like imagine sugar cubes, centimeter by centimeter by centimeter. If they were packed perfectly in this box, they would all fit inside. something to think about in terms of cross sections. If we take a cross section of this box parallel to the base, right? So we cut through with a plane. What will we find about that cross section if a plane cuts through the box? And again, so my cross section is parallel to the base. What can you tell me about it? Yeah, it's the area of the base, right? Yeah. So, so when we talk about cross sections, we're talking about cross sections of some plane, and then if we move that plane vertically, we will scan through the volume of this box. Okay. Integration is all about accumulating stuff. So if we add up all of those cross sections, that should generate the volume. So we could look at this right here, the volume, as the integral of the area of the base as we go from 0 to whatever the height is. Okay. And let's say y is going to be our vertical, our perpendicular measurement here. So let's call that dy. So in this case, what would that look like? Well, my base is 5 times 8 centimeters squared, which is what, 40 centimeters squared? And so if we were going to integrate from, as y goes from 0 up to 5, right, for the height, 40 dy, what's going to happen there? We'll get 40y is the antiderivative, right? And evaluating that at 5, we get 40 times 5. Evaluating it at 0, we'll subtract 40 times 0. So ultimately, we get 40 times 5, which is 200, which is the traditional volume formula we know, length times width times height of a box where you have all these right angles going on. So we can use integration with cross sections, and we can generate volumes of things. Okay. Sometimes that's easy to do, sometimes it's hard to do. It depends on the thing we're working with. Another example that we could use in terms of a cross section, actually let me do rotation, then I'll come back to cross section. Imagine in the XY plane, there's Y, there's X. Let's take, for example, this line right here, which I'm going to say is the line y equals 3. And then imagine holding your fingers on the x-axis and that you could pull this out and then spin while holding the x-axis. What would this line be sweeping out as we spun through the x-axis? So we want to revolve around like that. What would we generate if we did that? We'd generate a cylinder, wouldn't we? Yeah. So if I draw it out in red here, come down 1, 2, 3, it's going to sweep out of the screen and then back into it again. It'll come back through down here at y equals -3. And what we'll find is that we've swept out a lovely cylinder as we do that. Now, the cylinder is sideways here, but it has a base, right? Right there. And can't we identify the area of that base? Okay, so I'm going to look at this in 2 different ways. So one way to look at it would be to say, well, I have, and what can you tell me about cross sections perpendicular to the axis? Do they have any relation to the base? They're the same thing, aren't I, right? So any cross section I take here is going to be that same area right there. Okay, that's the area of a circle, and so I know that the area of a circle is pi r squared, so that's pi times 3 squared, or you could say it's 9 pi, right? And if I were then to integrate from, if this is the base, all the way through to its top, isn't that the same thing I did over here for the rectangle? Except I'm just doing it sideways. Okay, so let's see. Let's suppose that I'm going from, I don't know, x equals -2 here, And maybe this is what, 1, 2, 3, maybe that's 4, all the way up to x equals 4. So then I would have the integral from x, oops, I didn't mean to put a 0 there, erase. The integral from x equals 0 to 4 of, it's a constant cross-section all the time, isn't it? It's always 9 pi, right? So I'm just integrating 9 pi with respect to x. I wrote that 0 again. Why do I keep doing that? Because 90% of the time our homework in the last chapter, we started off with 0. All right, sorry, -2. There we go. All right, so that's going to give me 9 pi x as the antiderivative. And so then I'm going to evaluate 9 pi x as x goes from -2 to 4. And squeeze that in down here, maybe a different color to help separate it. So that's going to give me what, 9 pi times 4 minus 9 pi times -2, which is going to give me what altogether? 6 times 9 is 54 pi. Does that sound right? Yes, no, maybe. Anyone else get that? 54 pi? So I think the volume of this is 54 pi. Another way to think about it, given a particular cylinder, if you know the radius and you know the height, the volume of that cylinder is going to be essentially the area of the base, pi r squared times the height, which is what we've generated here, right? Isn't the height of this thing 6? Sideways height? Radius is 3. So that's kind of the traditional volume of a cylinder. We came about it a different way. Okay, I'm going to look at it one more way just for fun, because I haven't quite followed through on my rotation. We visualized the rotation and saw the cylinder, but it turns out there's another way to look at it. So again, let's go back to this sketch here. Switching colors, y equals 3, and we are going to revolve this through around the x-axis. When I do that, I'm going to generate this 3-dimensional cylinder here, rough sketch. And I just want to imagine a chunk taken out of this right there. And what's that chunk look like? Well, looks something like that. I'm going to call the width of this thing right there, I'm going to call it dx. And we know the basic idea of any kind of area like this now, that if we take the height of it or the width of it, that's this right here, and we multiply by the area of the base, then we can start generating volumes. Okay, so we started building that idea. Now what I'm going to take here is this y is really some function f of x, right? And wouldn't you agree that this is the radius of my cylinder right there? And function-wise, the radius of my cylinder is my function value. Okay? And so if I use that as the radius, then my cross-sectional area, let's call that delta area, is going to be pi times f of x squared. Right? Because area of a circle is pi r squared. R happens to be being pulled from the function values. Now here the function's kind of boring. It's always 3. But we can do this with anything. So we'll try a different one in a minute. So if I then take this into its limit and sweep my integral through, then what I'm going to get is the integral as x goes whatever starting point A to some other starting point B, pi times f of x squared dx. So this is kind of a general idea we can use for any function. It doesn't have to be just a cylinder, We can rotate any curve around some axis and generate a three-dimensional object. Okay. Anybody ever play with clay and make a bowl in a pottery class? You put it on a little spinning wheel, right? And you use that spinning wheel to make your solid. That's what we're doing here. The thing we're doing that's a little bit different is not only are we going to try and visualize the solid that we make, but we're also going to calculate its volume. And pi is almost always going to pop up because we're rotating something. And anytime you rotate, pi is involved, which is kind of neat. Okay. So some of our solids will be found by trying to take cross sections and sweeping those cross sections through a region. Other times they're going to be found by spinning some function around an axis. Sometimes it'll be the x-axis, sometimes it'll be the y-axis, but it could be any straight line, really. Doesn't matter. Okay. The task then is discovering, if you rotate, what's the radius? That's always the hard part. Once you get that, then you just have to find an antiderivative. And either we can or we can't. All right, so we'll come back to rotational solids in a minute. Let's go back to cross-sectional solids. And let's see, I had one in my notes I wanted to look at. Where did I put it? Here, maybe? Yeah, that one's a cute one. All right. So I'm going to sketch this out for a second time, but the one challenge we're going to have is drawing. Because we're going to try and visualize the things we generate and draw us pictures of them. And it's always going to be a challenge. So here's what I got. I have this parabola, which is x equals y squared. And I can break it down into two square root functions in terms of y equals the square root of x and y equals negative square root of x. Okay. So next thing I want you to visualize is imagine a square perpendicular to this plane right here. Okay. And then we're going to twist that square so that the diagonal of the square here stretches between symmetric points on that right there. So what I'm going to have are these looks like these triangles sticking up here. Okay. And so my claim is if I sweep that square through perpendicular to the x-axis there, I'm going to generate a figure that looks like this bottom one here. Okay, it's a bowl. That bowl has flat sides, but the corners are parabolas, half of parabolas. Okay, so let's try sketching this together and see if I can get you to agree with me. And then we're gonna try and calculate the volume. And my claim here is I have some algebra here that calculates that volume. Okay, so I'm going to walk you through my sketch. So let's give it a shot. First thing we need to do is sketch the functions involved. So we need a sketch of y squared equals x, which could be rewritten as x equals plus or minus, oops, sorry, wrong way. Y equals plus or minus square root of x. And let's get out of the red color. So y equals plus or minus the square root of x. And we're going to do this, we're going to take a look at the interval as x goes from 0 to 4. So 1, 2, 1, 2, 1, 2, 3, 4. Always a good idea to label stuff. And we're going to start doing all kinds of crazy stuff geometrically. So we always want to label each axis to keep track of what's going on. All right, so sketching my graph here. I got the point 0, 0, the point 1, 1, and the point 2, 4, somewhere up there. For the positive square root, and the negative square root has also 0, 0. It will have 1, negative 1, and 4, negative 2, right? And so here's my sideways parabola. Something like that. And now I'm trying to visualize 3D sitting on 2D here, right? So what we're going to do is, let's pick, I don't know, this point right here and draw a line in between there. And then I want to visualize that being half of a square sticking up, and so the other half is pointing through the wall here, through the screen, down here. Oops, that came out very sloppy. Let's try it again. Something like that. Now try to squint and make believe it's 3D. Okay, so that's coming up out of the screen. This triangle here is not flat. It is perpendicular to the screen. With me? And then we're going to sweep that through the x-axis. So that means at the end here, there will be a similar square sticking up. The main diagonal of the square cuts right through the axis, and then part of it is sticking back here, perpendicular. Tough to draw. So if I rotate this 180 degrees, it could hold water. Right? It's a dish of some kind, a very strange one. Wouldn't sit up very well because of the parabolic bottom. What does the top of this dish look like? What is it? It's a square, right? So I could just try and draw that rotation, and I'm going to draw the square so that I'm like, looking at it in 3D. It's going to look something like this. So let's say that's my square top. And maybe the bottom of it lives down here somewhere. And coming down to that are these parabolic corners. Something like that. And this one in here is going to be coming down at like a parabola. Okay. Now, since I am sweeping the square through the x-axis, squares have straight sides, right? That means like this side right here is flat. This side right here is flat. Every side on this sucker is flat. But these corners, what are the shape of the corners again? They're parabolas, they're half parabolas, yeah. Okay, so that's the object we're building. So in order to do so, I need to come up with an equation for the surface area of any one of these squares. So what is the surface area of any one of these cross-sectional squares? Because anytime I slice through this perpendicular to the x-axis, I get a square. Okay, well, let's see. So I'm going to draw it again. So this is, again, the hard part about these guys is setting them up. So here's my square. And I decided that it was the diagonal of the square that I'm going to measure using these two curves. So, well, let's see, what's the top here? Well, the top here, that's the square root of x, right? What's the bottom of that diagonal? It's the negative square root of x, right? And if I want to find the distance between the square root of x and the negative square root of x, I subtract them, right? So that means my diagonal, d, is equal to the square root of x minus the negative square root of x. What does that clean up to be? 2 square roots of x, yeah, so that's 2 square root of x. Okay, now I need to find the area of this whole thing, and usually when I find the area of the square, don't I find the side length s and its area? Isn't that always s squared? Okay, so given the diagonal, how do I figure out what s is? What tools do we have to help us with that? Pythagorean theorem, right? This is a right angle. It says s squared plus s squared has to be d squared. Okay, so s squared plus s squared has to equal d squared. So on the left side, I'm going to get 2 of those s squareds, and on the right side, I get the square of my diagonal, which is what, 4x when I square that? Divide by 2 gives me 2x. And then s would be the square root of 2x Technically, it's plus or minus, but this is the length of a side, so I think we're pretty safe with the plus. And the area is the square of that. So any cross-sectional area here has to be the square of the square root of 2x, which is just 2x. So yeah, so any area is going to be 2x for this sucker. Now that I finally discovered the cross-sectional area, and that's always the hard part, setting these suckers up, now I can just integrate it, and that's the easy part here. So my volume is going to be the integral as x goes from 0 to 4. And remember, sometimes before I would write down my variable of integration with the boundaries, we're going to be switching variables a lot in this chapter, so it's always a good idea to write which variable you're playing with. Otherwise, things get confusing. My integrand is just 2x, and again, that is with respect to x. Antiderivative of 2x, x squared, right? That's not bad. And that's happening as x goes from 0 to 4. So that's going to be what? 4 squared minus 0 squared, which is 16 cubic units. Units cubed in this case, because I took that area and I gave that area a height. So units squared times units would be units cubed. That was cool. We built ourselves a crazy dish and found its volume. Any circles going on in this one? Yeah, so we could generate a different figure by rotating it and create a parabolic dish. Right? You ever see those sitting on people's houses? Dish TV? We could figure out if we let that collect rain and we knew it's a little bit of dimensions of it, we could figure out how much water it would hold by making a rotational one. So we'll do that in a minute. Let's do another cross-sectional area. And I'm doing this one because it blew my mind the first time I saw it. So bear with me on this one. So I need you to visualize something with me. I was watching some crazy show the other day, and they were running around the sewers underneath New York, and the sewer was this giant tube, right? And guess what happens in sewers? Well, they connect to other giant tubes, right? And so what I wondered when I was watching this movie, I was like, okay, so this guy's running through this tube, and then that tube meets another tube, and let's say for simplicity they meet at a right angle. If it's not a right angle, it gets a wee bit more complicated. Right? So the rest of my family is watching this, freaked out about what's going to be in the corner in the tube. And I was wondering, hey, what's the shape of where they meet? What does that look like? I was like, oh man, I could use like geometry to figure that out. So we're going to try and figure out what the intersection of two pipes looks like. And then we're going to try and find its volume. Okay. So one thing I was thinking about is if I were to take a ball that just perfectly fit in here and roll it through, it should be able to go through and change direction, right? Okay, so that means the volume inside has to be at least as big as that ball, right? Let's make believe like everything was perfectly greased and the ball was exactly the same size and it just slid, no friction, right? So I know that that intersection has to be at least as big as the ball. And there's formulas for balls. We'll calculate one in a little bit. All right, what's that look like? Okay, so I got the top-down picture to think about, so let's start there. So, well, looking straight down, it's a square. Okay, well, that's kind of cool. I'm really good with squares. So I know those pipes come in, and looking down at it, their intersection makes a square. Okay. And let's see. Down here, it's going to be like in the middle, right? Midpoint. Up here is the highest point on each pipe. So my square from the top, it's got to have some peak, and then it's got to drop down toward those corners. Wouldn't you agree? Something like that. Okay. And as I look down, I could imagine taking slices that are parallel to my top view. And I'm thinking that any slice I make is going to be another square. The biggest square will occur at the midpoints of the pipes, and those squares will shrink from the midpoint all the way up to a dot at the top. Right? Can't you imagine the top of the pipe? Isn't there a line that is the highest point on that pipe all the way down that line? Right? And this pipe has a line that's right at the top, and so that points at the top line of each pipe. Okay. So that's kind of cool. I know somehow I have square cross sections. What I have to figure out is what's the equation for that side S as I move up and down. Okay, so now I need a different perspective. What's going to happen if I look through the pipe? Well, if I look through the pipe, so now we're going to take, so this is again top view. Let's take a side view. All right, side view, that's going to be a circle, ain't it? Okay, and I know that it's widest right through there. Okay, that's like these midpoints up there. And then as I move up through that, right, I'm going to end up seeing this square cross section. You know, maybe that one lives right about there. Okay. Let's see. So let's, for fun, call this direction Y. Again, this is my side view. And let's call that one X in my side view. And so I want to try and figure out, this is my side length S, right? Can I find an equation for that? Well, if I just, you know, say this, isn't this 0, 0 right in the middle? And let's suppose that radius right there, let's just call it R for radius. What's an equation that would give me a point right there on the circle? And remember the equation of a circle? Centered at the origin, radius R. This is going to come up a lot, this chapter, section in particular. It's x squared plus y squared equals r squared. And so what I'm imagining is these cross-sectional squares, so that's a side view of my skinny little cross-section moving up, right? So this guy right over here, side view of that guy, very flat, thin guy. He's going up as y goes from 0 to, what y value would be right there? Oh, it would just be r, right? Yeah, so y is going to go from 0 to r. So that's going to be like my variable of integration for these cross sections. Okay, so I know I'm going to be integrating some thing as y goes from 0 to r with respect to y. Well, that kind of makes sense to me because this from here to here is a horizontal distance, isn't it? What variable measures horizontal distance in this plane? X, yeah, that's an X value right there. Okay, so then my side length, wouldn't that just be 2 of those X's? If I could just figure out what X is. Okay, so now I know, according to my side view, S is 2X, but my variable of integration is Y. Do we have an equation that ties X and Y together here? X squared plus y squared equals r squared. Yeah, that's the connection between x and y. Yeah, so if I just solve that for x, well, bring the y to the other side, so we'll get an r squared minus y squared, and then we'll have to take the square root. So we're going to get x is equal to plus or minus the square root of r squared minus y squared. Okay, so we're making progress. We're building our cross section. And I mentioned before, that's the hard part, visualizing it, building it. Okay, let's see, where are we? We know that the side length is going to be 2x, and we know x is that. Okay, so now I know that s is twice these square roots. And again, the minus is just, you know, that side, or no, what's the minus would be? Yeah, it would be that side over there. So let's see, I'm going to have 2 square root of r squared minus y squared. What am I sweeping through again? Cross-sectional thing is a square. So what's the area of that square? Side squared. Do we have the side? Yeah, square it. That's the area here. So let's switch colors again under here. So if this is the side length, then the area has to be that sucker squared. 2 square root of r squared minus y squared, all squared. And that is what I need to integrate. Interesting. Drawing this 3D object, now we have cross sections, right? We haven't actually drawn the 3D object. What does it look like? That's hard. So let's just come over on a new page and see what we have here. So I think I've got, let's see, blue is okay. The integral as y goes from 0 to r of that thing squared, which I think is going to be 4 times parentheses r squared minus y squared dy. Is that going to build the chamber I was seeing these guys run through on the TV show? Not quite. I just did the top half of that, right? Isn't the bottom half of that chamber the same, identical? Yeah, we have symmetry here, so I need to double that sucker. All right, doubling that thing. That should be the volume of the intersection of 2 pipes with the same radius, right there. All right, calculate it. See what you get. Clean that up, come up with an antiderivative, evaluate the antiderivative at the endpoints. The r's will not go away. You're going to be stuck with r's in the end here. Plugging in the right endpoint and the left endpoint, or upper and lower. I got a bunch of zeros. Let's see, what's this? This guy right there is r cubed minus r cubed over 3. So an r cubed minus 1/3 of an r cubed, which I think is 2/3 of an r cubed. Eight times 2. So I think it's 16/3 r cubed. And I said that should be a little bigger than a ball of the same radius, was my belief. We'll test that out in a sec, if I didn't make a mistake. Just some notational things. If your integrand is complicated, always put it in parentheses. Don't forget to note your variable of integration. R is just a constant as far as y is concerned. Maybe it's 2, maybe it's 8. Maybe it's feet, maybe it's centimeters. So Antiderivative of a constant is the constant times y in this case, right? Antiderivative of y cubed with respect, or y squared with respect to y is y cubed over 3. And it cleans up pretty nice. Anybody else get 16/3 r cubed? Okay, I got a couple nods there. So I'm just going to look up volume of a sphere. Does anybody remember that off the top of their head? Volume of a sphere. 4/3 pi r cubed. Okay, let's see. Pi is a little bigger than 3. And 3 times 4 is what, 12? How did we do in comparison? So that's roughly a little over 12 in the numerator versus 16. So is my space bigger than a ball of the same radius? Yeah. Okay. So 16 is bigger than 4 pi. Yeah. So it is bigger. Just to kind of double check that idea, looking through this way, although through the side view, right, the ball fits very tight in the side view. From the top view, that ball has some space. Agreed? That space is quite tight at the top, but there's more space in the corners there. So that's that extra space in the corners, that difference between 4 pi and 16. Okay, so there's a little space in there. Anybody want to take a shot at drawing this 3D figure? What does it look like? We know what it looks like from the top. We know what it looks like from the side. Right? If we look straight on the side, we'll see a circle. If we look straight down on the top, we'll see what looks like a square pyramidal type thing. But what does it look like if we look at it from an angle? Let's see. I'm going to do my best shot to sketch it, and then I'll show you some pictures I found online because I'm not the best sketcher. So if I look at it from kind of an angle, it's going to have, you know, a peak on the top, right? And then it's going to head down from that peak in a circular kind of shape. And when it hits its midpoint, there's going to be a straight line pretty much because it's got that square intersection. So there's going to be something square-ish about it. And then it, you know, it comes down from the other side, and maybe I'm looking at it from an angle. It's going to come down kind of like that there. And then there'll be a point underneath here somewhere, and it's going to come down toward that. Looks like kind of like a lid to a grill maybe that has a square. And there's that invisible side and back here that I haven't drawn. I wonder if I can draw that with dotted lines in a different color maybe. Let's see. You guys trying to draw this too? Don't make me the only one that suffers here. Anybody here a good sketcher? I am when I'm not under pressure, like there's not people staring at me. You guys are staring at me, making me nervous. So let's see, the square in back. So that would come down there, and then there's that side that eventually goes up there. That's getting hard to look at. Okay, I found some pictures online. Let's take a look at them. So, where did I put that? Here. Consider two pipes intersecting. All right, so here's the two pipes intersecting at an angle. And you can see that point we were talking about, that kind of curved pyramid. And here's an actual rendering of the 3D object, what it's going to look like right there. And let me blow that up a little more. Yeah, so that's kind of what it looks like. If I were better with 3D graphics, I would have loaded some kind of program that we could grab and rotate the object on the screen. That's always fun. All right, so that's what this sucker looks like. I did my best to draw it. So our challenges with the stuff we're doing right now are, can we attempt to make a sketch of the object? Sometimes, I don't know about you, if I had a piece of clay, I could probably shape it okay or carve it with a knife and a piece of wood. But drawing 3D on paper is always challenging. How many people find it easy to just draw a simple box on paper? Right? Some people are good at it, some people aren't. It's a matter of practice. Same thing with these shapes here. The more you practice, the better you get. A ball isn't that complicated, but draw a ball on a piece of paper that looks realistic, right? It's a challenge. Let's do one more problem, and then we're out of time for fun today. So there's a few problems in the beginning of the homework that say, here's what the cross-section looks like. Can you find its area and then integrate it through some distance? So we just did a couple of examples from easy to medium to very hard. That last one is in definitely the very hard category. Quick look at a rotational problem. Oops, can't spell rotation. Rotation. Volume. And let's see, let's make a parabolic dish. Why not? So let's take y equals x squared. And let's just look at it between -1 and 1. It's going to have a point there and a point there. If x is a half, y is a quarter. So it's going to look something like that right there. And what I want to do with this thing is if I'm going to make a dish out of it, I would choose to rotate about the y-axis. So this is my y-axis here. I'm going to rotate around that. Now, really, I don't need to rotate this whole parabola. I really only need to rotate half of it, because as that half spins, it will carve out my dish. Okay. So when I do that rotation, I'm going to end up with a circular top. Straight down below, there's going to be a bottom. And what is the shape of the edge of this dish? It's a parabola. Okay. So the top is a circle, but the edge is a parabola. Parabola. All right, so to do that, what I do is I imagine a little chunk of area being rotated. So I'm going to take a rectangle perpendicular to my axis. So this is usually the first step. This kind of rotational volume, I'm using a method called the disk method. And setting it up is the hard part. Okay, so the width of my disk is always dx or dy. In this case, it's a dy because it's a little chunk of the y-axis. Now, when I rotate it, I'm going to generate these circles, and so I need to identify the radius of those circles. Well, the radius would just be the distance from here to there, right? That is a horizontal distance. Which variable measures horizontal distances here? Yeah, so the radius is an x value. However, I'm integrating with respect to y here. So is there a connection to find a radius, an equation that will connect x with y? Well, usually you're given that connection. Yeah, so I just need to solve that for x. So x in this case would be plus or minus the square root of y. According to my picture, do I want the plus or the minus? I want the plus. Yeah, the minus would be the blue one on the other side. Yeah, so my radius here is the square root of y. And when I rotate that little chunk, that little rectangle, I'm going to end up with a piece of volume that looks like this. Let's call that delta volume. The height of this is just a cylinder, isn't it? A little chunk of volume. Yeah, so using the disk method, I'm either going to generate little cylinders or sometimes little washers. We'll make washers next class. That's my dy right there. And then to find this area, I just need pi r squared. There's r. So my little chunk of volume here is going to be pi times the radius squared times the height, dy. And so if I integrate, as y goes from, in this case, what, 0 to 1, that right there, cleaning it up a little bit, square root of y, the square root of y is y, right? So I'm going to get pi y dy from 0 to 1. That's easy to take the antiderivative of. The hard part was setting it all up, right? And so this, in the homework, your struggle is going to be looking at what you're given and trying to set up either your cross-sectional areas or decide on what is the radius for your little discs that you're building. Okay. And then we integrate those little thin discs across some height or length. And if we're out of time right now, but if we finish this, we will know how much volume that has, how much liquid it could hold, how much mass is in there, say. Okay. All right, so I'm going to stop there. We are still not done with 6.1. We still have some more complicated rotations to do, and we need to look at situations where we end up with these hollowed out figures instead. Okay. So for example, we might make a wrong way. We might make a washer type figure that looks like this. It looks like a cone, except what we'll do is we'll say we'll hollow that cone out with a cylinder in the middle. Okay. Can we find the volume of figures like that? Turns out that's actually not that hard. Okay. It's just a twist of what I just did on the board. Okay. All right. Go forth, do good math, physics, and other good deeds. I'll catch y'all soon. See you later, Gerald.